Today we'll study the linear Diophantine equation. Now any equation in one or more variables which is to be solved in integers is said to be a Diophantine equation. Now Diophantine equations, they may have any form and any number of variables. Here we are just going to talk about linear Diophantine equations, and the simplest of which is ax plus by equals c, where a, b and c are given integers in which a is unequal to 0 and b is unequal to 0. And in this we have to find integral solutions of x and y. Now before solving this equation, we need to determine whether this equation is solvable in integers or not. And for that, what we'll do is, for this linear equation, we'll find GCD of a and b. And suppose that GCD is d. Now if d divides c, then this equation will have a solution. And if d doesn't divide c, then this equation will not have a solution. So the first thing that we'll decide is whether this equation is solvable or not solvable. So all we need to do is simply take the GCD of a and b and check if it divides c. Now suppose this equation is solvable, that is when d divides c, in that case what we'll do is somehow we'll solve this equation to find particular solution x0 and y0, and then we can find a general solution to this equation by writing x as x0 plus b upon d into t and y equals y0 minus a upon d into t, where t is an integral parameter. Now if we have a general Diophantine linear equation such as a1 x1 a2 x2 up to an xn equals c, then again we'll check whether this equation is solvable or not. In that case, again what we'll do is we'll find GCD of all the coefficients a1, a2 and an, which is suppose d, and if d divides c, then this equation is solvable, and if d doesn't divide c, then the equation is not solvable. Now what we'll do is we'll prove this theorem. Now suppose we have this linear Diophantine equation, which is where a, b and c, they are integers and a is unequal to 0 and b is unequal to 0. Now we are looking for integral solutions of this equation. Now suppose GCD of a and b is d, then we can write this a as dr and this b as ds, where GCD of r and s is 1. Now if this equation is solvable, then suppose it has a solution x0 and y0, we can write ax0 plus by0 equals c. Now this a is dr and b is ds. So we can write d and then it is rx0 plus sy0 and it is equal to c, which clearly means this d, it must divide c. So this equation is solvable if and only if d divides c. If d doesn't divide c, then this equation has no solution. Now how do we find its general solution? Now once we have any particular solution, say x0 and y0, we need to find another solution. And for that, what we'll assume is, suppose other solution is x dash and y dash. Now we can write ax0 plus by0 equals c, and it must be equal to a x dash plus b y dash. Now we can rewrite this as a x dash minus x0 and b y0 minus y dash. Now we know that this a is dr, so it will be dr x dash minus x0, and this b is ds y0 minus y dash. Now this d will cancel, so we'll get r x dash minus x0 will be equal to s y0 minus y dash. Now we have taken GCD of r and s as 1. That means this r, it doesn't divide s and s doesn't divide r, which simply means that this r, it must divide y0 minus y dash, and this s, it must divide x dash minus x0. Now if we look at this, then we can write x dash minus x0, it must be some integral multiple of s. So we can write this as x dash minus x0 equals xt, or x dash as x0 plus s into t. Now what is s? d into s is b, then s is simply b by d. So we can write this general solution as x dash equals x0 plus b upon d into t. And if we put x dash minus x naught as st, then we'll get y naught minus y dash as rt, or y dash will be y naught minus rt, that is y dash is y naught minus r, and r is a upon dt. So this is how we find general solution to this simple linear Diophantine equation. Now let us take up some examples. Now this is the equation 2x plus 6y equals 2021, and we need to find integral solutions to this equation. Now here a is 2 and b is 6. Now GCD of 2 and 6 is 2, and this 2, it doesn't divide 2021. That means this equation has no solution. So this linear Diophantine equation has no solution. Now we'll take another example, in which is 5x plus 3y equals 4. Now in this case, GCD of 5 and 3 is 1. Now 1 clearly divides 4. So this equation will have integral solutions. Now in order to write its general solution, we need to find a particular solution, that is x naught and y naught. Now we know that 5 minus 3 is 2. Now we multiply it with 2, we can write 5 into 2 minus 3 into 2, it is 4. Now here we can write x naught as 2 and y naught as minus 2. Now this x is x naught 2 plus b upon d. Now b is 3 and d is 1. So it will be 2 plus 3t, and y will be y naught minus a upon d into t. Now a is 5 and d is 1. So it will be minus 2 minus 5t, where t belongs to z. So the general integral solution to this equation is x is 2 plus 3t and y is minus 2 minus 5t. Now let's take another one, in which is 5x plus 3y plus 1 by 3z equals 100, and x plus y plus z is equal to 100. We need to find integral solution to this system of equation. Now we'll find z and we'll put it here. So we'll write 5x plus 3y plus 1 by 3. Now we can write this z as 100 minus x minus y will be equal to 100. So we multiply it with 3, we can write 15x plus 9y plus 100 minus x minus y will be equal to 300, or we can write 14x plus 8y, and it is equal to 200. Now we'll divide it by 2. So we can write 7x plus 4y equals 100. Now we need to find integral solution to this equation. Now here GCD of 7 and 4, it is 1. So value of b is 1, and 1, it divides 100. So this equation is solvable in integers. Now we need to find one particular solution. Now we know that this 4, it divides 100. So 25 into 4 is 100. So one of the solution possible is, if we take x naught as 0 and y naught as 25, we'll get one solution. Now x naught is 0 and y naught is 25. We can write its general solution. Its general solution will be x equals x naught plus b upon d. Now b is 4 and d is 1. So it will be simply 4t. So we get x equals 4t, and y will be 25 minus, now it is a upon d. So it will be simply 70. So value of y is 25 minus 70. And this z, it is nothing but it is 100 minus x minus y. So it will be 100 minus 4t minus 25 plus 70. So it will be 75 plus 3t. So value of z is 75 plus 3t. So this is the general solution to this equation. Now if we have to find number of positive integral solutions to this equation, now for positive integral solutions, x is greater than 0, y is greater than 0, and z is greater than 0. Now from this first one, we'll get 4t greater than 0, that is t is greater than 0. Now from this second one, we'll get 25 minus 70 is 0, or t is less than 25 by 7. And here we'll get t is greater than minus 75 by 3. If we solve this, we'll get t should lie between 0 and 25 by 7. Now 25 by 7 is 3 point something. So the only integral values of t possible in this case are 1, 2 and 3. So this equation, it will have 3 positive integral solutions. Now if we want, we can write this solution also. Now if we take t as 1, then value of x is 4, value of y is 25 minus 7, and 25 minus 7 is 18, and 75 plus 3 is 78. In the same way, we can find solutions when t is equal to 2 and t equals 3. Now let us take another one, which is 141x plus 34y equals 30. And in this case, we find GCD of 141 and 34, this GCD is 1. So value of d is 1. And again, 1 divides 30. So this equation is solvable in integers. Now first we need to find x0 and y0 in order to write general solution to this equation. Now for this, what we'll do is we'll use Euclid division algorithm. Now we can write 141 as 4 into 34 plus 5. Now we'll take 34 and 5. We can write 34 as 6 into 5 plus 4. Now we'll take 5 and 4. We can write 5 equals 1 into 4 plus 1. And then this 4 is 4 into 1 plus 0. So GCD of these two numbers, it is 1. Now we need to find x0 and y0. Now we'll construct this equation from here. We can write 5 minus 4 is 1. Now we'll keep replacing this smaller term. So we can write this 4 as 34 minus 6 into 5. So it'll be 5 minus 34 minus 6 into 5. It'll be equal to 1. So it'll be 7 into 5 minus 34. It'll be 1. Now we'll replace this 5. This 5 is 141 minus 4 into 34. Minus 34 equals 1. So it'll be 7 into 141 minus 28 and 1. So it'll be minus 29 into 34 and it is equal to 1. So now we have 141 and 34 and we have this 1. Now we need 30 here. So we'll multiply everything with 30. Now if we multiply everything with 30, we can write 210 into 141 minus 870 into 34 and it is equal to 30. Now if we compare it with this equation, we can write value of x0 is 210 and value of y0 is minus 870. Now we can write its general solution. So it will be 210 plus b by d into t. So it will be 210 plus 34t, and here y will be minus 870 minus 140 1t, where t belongs to integers. So this is the general solution to this equation. So for particular solutions, we can use Euclid division algorithm. Now here the question is, we need to find integral solution to this equation, which is 8x plus 14y plus 5z equals 11. Now if we find GCD of 8, 14 and 5, it is 1, and this 1, it divides 11. So value of d here is 1. Now we need to solve this equation. So what we'll do is, we'll rewrite this equation as 2 into 4x plus 7y plus 5z equals 11. And now we'll let 4x plus 7y as some other variable, say w. So now we have this simple linear equation, which is 2w plus 5z, and it is equal to 11. Now for this equation, if we find GCD of 2 and 5, GCD of 2 and 5, it is 1, and 1 divides 11. So this equation is solvable. Now we can write 5 as 2 into 2 plus 1. Now 2 is 2 into 1 plus 0. So GCD is 1. So we can write 5 minus 2 into 2 is 1. Now we need 11. If we multiply it with 11, we can write minus 22 into 2 plus 11 into 5. It is equal to 1. So value of w0 is minus 22 and z0 is 11. So from here we'll get w0 as minus 22 and z0 as 11. Now we can write general solution for both. Now this w will be w0, which is minus 22, and plus b upon d. b upon d is 5, so it will be minus 22 plus 5t, and this z is 11 minus 2t, where t belongs to z. Now here we need solution in x, y and z, not in w and z. Now we'll put the value of w here. Now this w is 4x plus 7y. So we can write 4x plus 7y is equal to minus 22 plus 5t. Now in this case, GCD of 4 and 7, it is 1. So we can write 7 as 1 into 4 plus 3. Now this is 4 equals 1 into 3 plus 1. Now this 3 is 3 into 1 plus 0. So GCD here is 1. Now we can write this 1 as 4 minus 3. Now we can eliminate this 3. We can write this as 7 minus 4. So it will be 4 minus 7 minus 4 equals 1, which is 2 into 4 minus 7 equals 1. Now here we need minus 22 plus 5t. So we'll multiply it with minus 22 plus 5t. So it will be minus 44 plus 10t into 4 and then plus 22 minus 5t into 7, and it is equal to, now here we'll get x naught as minus 44 plus 10t, and we'll get y naught as 22 minus 5t. Now here we can write general solution. So it will be x naught, which is minus 44 plus 10t and plus b upon d. Now here b upon d is 7. So it will be plus 7s, and y will be 22 minus 5t minus a upon d. So it will be simply minus 4s, where s and t, they are integers, and we have already worked out z. Z is 11 minus 2t. So this is the general integral solution to this equation.